So this part, I will discuss and describe our participation in the CASH challenge, dedicated to development of new compounds for receptor for which previously there were no active molecules at all. So what is the competition in general? So this is a competition between 25 cheminformatician group across all over the world, which were selected to participate in the first challenge. The main idea and intention of organizers was to encourage development and improvement of computational tools and methods, to provide prospective validation of those approaches to better understand their applicability, advantages and disadvantages. In long-term perspective, they wanted to create a platform to continue this challenge in future, and these days there already fifth challenge was announced recently. And for first challenge, they selected a very hard target, because before that there was no active molecules identified for this target. And as a secondary goal, all developments and achievements during this challenge should be made open to the public to facilitate and support open science. So all developments, all molecules do not cover any IP rights by authors, so they contributed to the public. Our motivation to participate in this challenge was to develop and validate our own internal pipelines and establish robust pipelines to be applicable in future projects, because we also work in this drug design field. So the first CASH challenge was dedicated to particular protein kinase LRK2, leucine-rich repeated kinase 2, which is involved in Parkinson's disease. And the goal was to develop molecule which can bind to particular domain of this kinase. I will show you the structure of this kinase. It's really large molecule. And they wanted to target this particular domain to design PROTAC compounds in future to combat the Parkinson's disease, finally. Here is the structure of this kinase, and this in blue are a particular domain for which we had to find some molecules. As you can see, it's like a donut with a large pore inside, and the binding site probably is somewhere in the middle. And this creates the first challenge, because we don't have anything except the crystal structure of a protein in unbound mode. The second challenge came from the complexity of a chemical space, as I already multiple times said, talked about this. So the wall size is very large, but in this particular case, they asked participants to select compounds from Enamine real database, which at that time was around 16 billion compounds. And this also is computationally challenging, how to do this in a proper way. So it's quite a large number of compounds to just simply screen all these compounds and simply dock all of them to this particular receptor. However, it is feasible, but it will require a lot of computational resources. Additionally, organizers apply some additional restrictions on molecules, so they prefer to design molecules with low molecular weight, lipophilicity, and so on, in order to find hits which are developable in further optimization studies and steps. Here is the whole pipeline of the challenge. So there are two major steps. On the first stage, we had 2 months to propose our compounds to Enamine. After that, those compounds were synthesized and tested. And on the second iteration, groups which succeeded on the first stage and found at least one active molecule, they should optimize in some way this structure to get better compounds finally. And again, we had just 2 months to do that and repeat the cycle of synthesis and experimental validation. And results were published just 2 weeks ago, final results. So how this domain looks like in dynamic, because since we have an apoprotein, we wanted to better understand the flexibility of this domain and sample for future structure-based modeling. So we perform classical simulation in multiple runs, in several repeats, selected some representative structure, and more or less understand how flexible this protein is. So for the first stage, we used strategy which I briefly told you previously based on our CREM structure generator, and we tried to design compounds completely de novo. So in this case, we used some initial fragments, we dock them into the receptor, select the best scoring fragments, then grow them using the CREM approach, generate new compounds, then dock them to the same receptor, choose the best one, and so on. So iteratively, we grow the ligand inside the cavity to fit all these protein features. Here I can skip these slides because I already showed it previously, so this I also can skip. I also took a lot of these issues on the synthetic feasibility because I already quite extensively explained and show you how you can tweak using the different databases, so of fragments and this context radius as well. We made some preliminary investigation of this tool to better understand its applicability. And again, what we discovered that if we use, as I previously told, more restrictive fragment databases for more synthetically accessible molecule, we observed improvement in synthetic accessibility score. Here is every point is the average of synthetic accessibility score and docking score across 100 top scoring compounds in every run. So we made multiple runs for CDK2 receptor as a model because we just wanted to understand how our tool works. And we discovered that, yes, indeed, using more restrictive databases and larger context radius, we can generate more and more synthetically feasible compounds according to this SA score suggested by Peter Ertl. But in those cases, we observe worse docking scores. And we had to find some threshold, some trade-off between synthetic complexity and docking scores. And we found that compounds which were generated with radius 2 and the most restrictive database were pretty good in this case. So these are just preliminary investigation of our tool. Next, we also wanted to understand, does it make sense to use for de novo design multiple structures of a protein sampled from MD simulations? And we chose 4 different structures of CDK2 receptor in complex with 4 different ligands. And we again repeat this de novo generation and analyze the output. Again, here is the average of top 100 compounds according to the docking score and average in synthetic accessibility score. And as you can see, the synthetic accessibility score, if you use the same constraints, they are pretty similar across different runs, but docking score is pretty much different. So that's why it suggests us that using multiple protein structures might be reasonable in that case because we can miss some good compounds in this way. Also, we repeated all these runs in triplicate to better understand reproducibility because it performs stochastic search. And here we count the number of unique Murko scaffolds in top 100 scored compounds. So these numbers means how many unique scaffolds were discovered within each run. So 11, 7, 20, and so on. And in these cells, you can see that there was no intersection between different runs and different proteins. And even within the same protein, the intersection of scaffolds was pretty low. So again, it suggested us that it is reasonable to run this program probably multiple times for multiple receptors to get better prediction and better cover the chemical space. So this was just the preliminary investigation. So now let's back to our particular goal within this cache challenge. So at the first stage, we had to select some initial fragments which will be used to growing. We can choose these fragments from Campbell, PubChem, whatever. But since those compounds should be synthesized by Yenamine, we decided to choose again starting fragments from Yenamine because, as it was shown previously, those chemical spaces, enumerated chemical spaces from different vendors, they are not so much intersect with each other. So that's why it is more reasonable to take starting fragments from that vendor which will be asked for synthesis of those molecules. So we selected 22,000 Yenamine fragments according to these rules. So they should have limit molecular weight, lipophilicity, number of hydrogen bond donor acceptors. Then we dock them to this protein and grow using the CREM. And for growing, we use the fragments obtained from the Yenamine stock compounds. So we took these 2.5 million compounds available in stock for Yenamine, fragmented them extensively. We also limit the synthetic accessibility score of those compounds to be on a safe side, to generate more synthetically feasible molecules as output, and the whole size of a database was up to 1 million fragments. So, and this procedure repeated multiple times iteratively to get final outputs. And here is a general pipeline which we applied. So we had a crystal structure of a protein. We performed MD simulations using StreamMD tool, with which you are already familiar, I hope, after yesterday's tutorial. And we selected 3 representative protein structure from every simulation. Then we performed de novo generation using docking algorithm. Using this developed software, we obtained 4 different hit lists for every of those proteins. We combined them together, and in total there was about 1 million molecules which were designed and docked. Afterwards, we filtered them according to the physicochemical criteria suggested by organizers. So it reduced quite a lot, this list. And also we filtered them by synthetic accessibility score to increase the chances to find some good molecules. And finally, we redock all these lists, not all these lists, but we selected top scoring compounds belonging to different scaffolds. And we redock them by multiple programs because this docking was guided by Autodock Vina. And in this case, we applied Vina, Gnina, Vinardo from Smina, and Glide. And we dock in every of these proteins. So we made 16. Yeah?
Why do you have 4 different lists of hits after the clean docking? Like, how did they split?
From every protein structure. We have its own list of molecules. So
why 4?
What?
Why for 3 proteins do you have?
No. Here is you probably do not see. Here is a line. So we also use the crystal structure of a protein. So we use the crystal structure of a protein as well, in addition to these structures obtained from MD simulations. So we get these 4 lists. So finally, we rescore these top scored compounds by multiple programs in multiple proteins. And what we found that those docking scores are uncorrelated. It's pretty common. So you use different docking programs, different proteins, different protein structure, and correspondence is very low. That's why this consensus might be useful, because it may somehow compensate these errors of particular docking algorithms. And to make a consensus, we used so-called exponential consensus ranking. So this is a specific type of aggregation function which prioritizes compounds highly ranked in at least one of the list, because we have 16 hit lists and we wanted to combine them in one hit list to select top scoring molecules. So we applied this ECR ranking. And further, we selected 400 compounds, which were rescored using the MMGBCA approach, again with the StreamMD software, which is pretty convenient and fast to do. And finally, we selected compounds belonging to different Murco scaffolds. And for every Murco scaffold, we selected top scoring compound. And in all this pipeline, there were no human interventions. So all these steps were done purely computationally. We didn't make some manual selection or visual inspection. At least we didn't interfere in the process. So we just look on these structures, look on these poses, but we didn't make a decision based on our knowledge. So we selected 50 compounds, finally. This is the first part of the first stage. And these are examples of those structures. So they do not look bad. So they should be, at least some of them, synthetically accessible, because all of them had synthetic accessibility score below 3. And for 11 of them, we could reconstruct retrosynthetic pathways by AZ-Finder algorithm. But as a second strategy to select compounds, we suggested the next one. Because we wanted to select some useful compounds from this large database, and we do not want to screen all of it. And we already have these nicely scored de novo generated compounds. We can use them as templates for similarity search. Similarity search, as I told you, is very fast. And that's why this procedure is extremely feasible. So we use our previously generated molecules as template, return the most similar compounds. And we apply this approach. So we perform similarity search using F-trees. This is a software from Biosolve IT. It calculates similarity based on some kind of 2D pharmacophore fingerprints, or at least representation, not fingerprints. For every compound, we selected 1,500 compounds. The most similar one, we combined all these lists, so we get 64 compounds in total. We again filtered them by the physicochemical criteria suggested by organizers, and we repeat the same procedure. So we made consensus docking using the EasyDock, then consensus ranking, and pose rescoring using the MD simulations. And we selected 100 top-scored compounds, again belonging to different scaffolds, to better sample the chemical space. And again, there was no human intervention in this pipeline. And here is the experimental results. So finally, we submitted 150 compounds for consideration. Then, within the given budget, because every project has its own budget, we selected 91 compounds for synthesis. 82 compounds were actually synthesized and tested, and 8 compounds demonstrated some activity within this range of values. And here are their structures. So they are not that highly active as one could expect, so we didn't discover any nanomolar activity compound. But at least we discovered 8 of them with a hit rate about 10%, which is already pretty well. And if you look at these structures, you can see some common features, like this one, this pattern, occurred quite frequently. And for the next stage, we decided to focus on this pattern to optimize compounds further. What we do next, on the next stage, so we tried, my idea was to identify true binding mode of our top scoring ligands, and then use some FAP perturbations to design and improve their activity or selectivity. And that's why we tried to use metadynamic simulations, which can be considered as an enhanced sampling of a protein ligand complex, so you can observe multiple times binding and unbinding events, and this gives you better understanding of the energy landscape, so you can locate your preferable binding pose, and so on, and calculate even true energies from these simulations. We had some complications because our compounds exist in two tautomeric states. So this pyrazole, we do not know which nitrogen is protonated, so we tried to simulate both of them. And unfortunately, there were some mistakes in setup, so we couldn't finish this result. So we found this mistake. We rerun the computation from scratch, but already we didn't have enough time because we are limited just 2 months, and we already spent about 1 month on metadynamic simulations until we discover this issue. Because metadynamics is quite sensitive to the setup, so some minor mistakes could result in wrong results. So, but nevertheless, we were able to sample better our protein in a complex with a ligand, and this could help us somehow on the next steps. We also re-evaluate our docking approaches, which we used for docking of molecules on the previous stage, on stage 1. We pass all these molecules to these docking algorithms and showed that in some cases we observed quite good discrimination ability between active and inactive molecules. If we particularly focus on some pyrazole derivatives, so active and inactive pyrazole derivatives, which were identified within our first stage submission, we got sometimes very good results. But again, you should take these results with care, so it's just the best one. Here I just plot some AUC values for different protein structures, because we took some representative structure from the metadynamics and add these representative structures to the previously identified 4 representative structure on the first stage. We used 3 different programs, Vina, Gnina, and Vinardo. And it was quite interesting to discover that, for example, Vinardo couldn't well separate those molecules which were identified on the first stage. So these green dots mean that AUC values here is 0.5, here is 0.5. So almost in all cases, they were below than random. And what we also tested here on this axis is different generators of conformers, initial conformers before docking. So usually we use RDKit, but for some reason we decided to use Chemaxon as a starting conformer generator. And what we discovered, it was quite surprising for me, that Gnina works better if we supply starting geometry obtained from Chemaxon, and Vina works better if we supply starting geometry from RDKit. I don't have a clear explanation, this is just an observation. So just to know that even your starting generation, starting conformation may affect your output for particular programs. So it's also quite difficult to predict which one will be better. And at the second stage, we applied several strategies how to select those compounds which more favorable properties. Since we are already short on time, we applied 3 strategies. One of them was a 3D ligand-based pharmacophores. So we had this actives one, this inactives one. We used our PSearch software for 3D ligand-based generation. It is very fast. It could help us identify some potential features. I didn't show you 3D structures, just on a 2D structures to demonstrate which features were considered as a common for actives and inactives. So we obtained quite good results according on the test set, some good enrichments, okay. And finally, we use the most restrictive pharmacophore model to screen the whole enamine stock compound library to select something similar. And finally, we selected 150 compounds with this approach. Another opportunity was just to perform substructure search. So we decided to explore the chemical space around these pyrazoles connected by a carbonyl group. So we selected all compounds having one of those substructures, and we found only 18,000 compounds, and they were also added to the final pool. And additionally, we enumerated structures using some ideas. So this was our top molecule, which we selected as a reference one, and we decided to decorate this piperazine from one side with the pyrazole carboxylic acid, from another side with ordinary carboxylic acid. So we retrieve all carboxylic acids from Yenamine library and all pyrazole carboxylic acid from this library, and combinatorically enumerate all possible structures. So we finally got almost 3 million compounds, which they were filtered by the physicochemical criteria suggested by organizers, and we got 200,000 compounds finally. And here we had to score these compounds, and since the time was shorter and shorter, and our, unfortunately, computational time on Karolina was also almost depleted, so we had to cut corners at this point already. So we before docking, we performed similarity search to the reference ligand using atom pairs, fingerprints, and we selected from the enumerated subset just 50,000 compounds, 1,000 compounds from substructure search, and all compounds which were retrieved by the pharmacophore search. Then we enumerated tautomers, stereoisomers, and dock all these compounds, but already using just two programs, Vina and Nina, because they demonstrated the best performance on the compounds from the previous stage. And we again aggregate those predictions using the ECR ranking, and we already didn't have time to rescore with GBCA model, so that's why we use these predictions as the final one. And finally, when we selected compounds, I already here in this at this stage I already apply visual inspection, and I already choose manually compounds for synthesis and for experimental evaluation, considering to better explore the structure-activity relationship. I tried to select compounds with different pharmacophores around these scaffolds to better explore, better understand the structure-activity relationship finally. And here is 37 compounds were submitted, 35 were synthesized, 4 compounds demonstrated dose-response effect, and one scaffold was confirmed as selective and selected by organizers as a top compound from our side. So this is a structure, and unfortunately its activity is not that much relatively to these reference compounds bearing similar scaffolds, so we couldn't improve their activity. And there are a lot of molecules were inactive. Yeah, please.
In the previous round, you are talking about binding demonstrated by SPR, and now you are talking about dose response effect.
No, they measure this dose response effect using SPR as well. And in the previous case, because I also demonstrated these IC50 values, they were also obtained with this technique. But they also, for those hits, they apply orthogonal assay to demonstrate that those compounds are really bind. Because they are weak binders, not only our compounds, others as well. And that's why they apply some NMR or calorimetry just to additionally support these evidences. So, yeah, this structure, just one, was selected as a good one, okay, but we couldn't improve the activity at after the second stage. So for me, it's quite interesting because after all results were published, I didn't see probably any group which could improve their predictions from the first round. It was quite surprising for me, but it's still interesting topic. So here is the overall statistic of all groups. Unfortunately, I couldn't find the identifiers of all groups which were in the gross list because they supply us with this preliminary result, and the last, the final one, and the general statistics, according to the number of molecules, they do not provide exact names of these groups. I just wanted to point you out that after the first stage, we discovered 8 hits. That was the third result among all these groups. There are just 11 or 10 hits more. And what was also interesting is that the group which discovered 11 hits, they discovered 0 hits after the second round. For me, it was quite surprising. So from 11 molecules, they couldn't optimize at least one or find some reasonable structure-activity relationships around those hits. So it may happen. So, and finally, all these groups were ranked by the expert in net cell chemistry, in biophysics, and computational chemistry, which are well known. And according to this rank, they summarize all scores from different groups. And here is the final list of, I would say, winners, because they selected top 3 places. So the first 2 places were split between David Kois from University of Pittsburgh and from Alexander Isaev in collaboration with Artem Cherkasov. The second place possessed by Christina Schindler from Merck, and the third place were split between 4 groups of Dmitry Kiriyev, Christophe Gargula, Didier Onyan, and my group. So, and all we have the same score. So they didn't discriminate very precisely. So I'm pretty happy with this result. So to be in this list of top scoring groups, because we left behind us a lot of other famous groups in chemoinformatics. And I tried to analyze these results. I just started because they were published just recently. I just started to analyze what structures were discovered by other groups. And it's a little bit mess, this data set which they provide, but I found that these compounds were labeled by expert as a promising one in some way, so they provide clear dose-response behavior, or they are good in orthogonal assay, or they have good medchem properties for their point of view. And these are compounds which were highlighted for the top performing groups from the David Kois, this molecule. For some reason, it has quite low affinity, so I don't know why it was selected, but probably there are some reasons behind. There are just some explanations were provided, of course, but I would like to talk to this expert maybe during this workshop, not workshop, symposium, which will be organized in 1 month in Toronto, who held all this experimental part on their site. So they collected all these top participants in this symposium and people from industry just to exchange their opinions, our results. So we will be able to discuss and all these questions. So the second group from Isaev and Cherkasov, they resulted in this molecule with pretty high affinity. From Christina Schindler, they also found some nice, from my point of view, it's a nice structure with moderate affinity value. So, of course, deeper analysis is required to better understand as these compounds are really bind or not bind, because they already started X-ray analysis. They co-crystallize one ligand with this protein domain, and what they found, unfortunately I forgot to insert this into the slide, that a ligand binds somewhere outside of this central cavity. And they still do not know is this an artifact or not. So it is still questionable where this compound binds. And this target, in my opinion, is really difficult because there are not so many polar contacts inside this cavity. There are almost only backbone atoms, like carbonyls and NH groups. There are just one serine, one cysteine group, and one tyrosine group, which is quite close to the outer region of the pocket. So it's not so probably drug-like, this central cavity. So as an intermediate conclusion, what I would say is that you always should have a plan B, because when I trusted that we will get results with metadynamics, we didn't develop alternative pathways and we didn't apply alternative strategies to generate those molecules. And that's why we were short in time on the second stage and we didn't have enough time to rescore and better prepare those outputs. So that's very, very important lesson. Don't trust these tools. And what is good that on the first stage, we demonstrated that fully computational pipeline without any human intervention was able to efficiently discover hits from the very large, I would say ultra-large chemical library. And our strategy based on the de novo generated templates was successful. So we achieved almost 10% of hit rate, which was one of the highest across all groups. And we confirmed that this consensus approach where we applied molecular docking in multiple targets and rescoring with GBCA approach was successful. This pipeline is now almost automated, or at least semi-automated in many aspects. And this project really helped us and accelerated us to develop internal tools for high-performance docking and high-performance MD simulations. And just few words about these tools, because EasyDock we didn't present during this workshop, but I just want that you know about this. So these are just interface to dock compounds on multiple servers if you need. So it allow you distributed computing with Autodock Vina, Gnina, and Smina, and all scoring functions which are implemented in Smina currently. But it can be customized with any other docking program if you want. So it's quite easy to customize. We also enable support of docking of boron-containing compounds because one of the group, they suggested exclusively boron-containing compounds as binders of this protein. So, and since after the first stage, organizers asked us to rank compounds of all other groups, anonymously of course, we had to somehow handle this boron-containing molecules. So we suggested the automatic protocol when we replace boron atoms on the carbon atoms before docking, and after docking we return it back. And we demonstrated that this strategy works nicely, and in redocking of known boron-containing compounds, we achieve results exactly the same as for normal compounds without this replacement. Some software like Gnina can handle boron atoms by design, but for example, Vina and Smina cannot do this. So if you have a boron-containing compound, they will just return you an error. In our case, we solve this issue. And we make this distributed over a cluster of computers, so it's very easy to run. Just one command line and that's all. Nothing else is required. We also optimized this pipeline with a specific priority function. So we tried to dock first compounds for which docking time predicted the highest. So we want to dock first the compounds which take long time. And at the end, we wanted to dock compounds which will take just few seconds. In this way, we optimize the tail computation because, for example, if you occupy 10 servers and your compound one docking lasts, for example, half an hour, and this is the last compound, all other servers will be occupied until this compound will finish its docking. That's why we prefer docking later compounds which are faster to dock. And we develop specific function which predict this docking time quite accurately. For different programs, it even can be scaled and transferred to other scoring functions, not only to Vina, because we train it on Vina, but it is applicable to other docking programs as well. And we demonstrated that we get almost 10% speed up using this priority function on 20 servers. Yeah. I'm a little bit. Yeah. We also optimized the number of cores and number of molecules because this was tested on servers with 32 cores, and we optimized how many molecules should be docked in parallel with how many cores per molecule. So we also optimized these properties, and in this case, the speed up was not so great, but it is still observed. And here is the overhead of our distributed Dask library implementation relatively to the ordinary multi-processing. So overhead was quite low on a single server, but even on a 20 servers, the overhead was pretty low, so below 5%. So people from the computer science told me that, oh, it's perfect. So I'm not so sure, but okay, I believe them. So it's a good result. And the next tool, which was developed during this challenge, or stimulated, which development was stimulated, is a StreamMD. So in details, Alexander told you a lot about this tool. So it performed high throughput MD simulations of complexes, of pure proteins, of pure ligands maybe, even with cofactors as well. So you can add some ions or additional like ATP, ADP molecules additionally. All those interfaces, I mean EasyDock and StreamMD, are easy to apply. So you just need to run one command from the command line, and that's all. And they can natively continue interrupted calculation, because if in a cluster you have a limited time per job, your job is interrupted during the reach out the time limit, you can just restart your script and it will continue from the point where it stopped. So it's pretty easy to use and pretty nice tools. Here is a list of softwares which was applied or developed during this challenge. So feel free to use it. Not all software are published yet, but we mainly publish all our tools as open source. There are some third-party software which was used during this challenge. And here is a group of people who participated in this challenge, because of course it is impossible to do everything by a single person. So these are my PhD students. Some of them are present here, collaborators from Prague, who perform these metadynamic simulations, to which and we now continue these simulations. And what is interesting, just the last point, we now continue these metadynamic simulations because I finally want to answer, could we perform better or not? Can we really discover true binding pose using metadynamic simulations? Now we collected more than 1 microsecond trajectory, and it is still not fully convinced that we know the exact binding mode of our compounds. So we already observed several binding and unbinding events. We already observed quite nice energy surface, but we tried to validate found minima in the classical MD simulations, but it is not all fully confirmed by these classical MD simulations. Sometimes ligands started to flow somewhere away. So we are still in a way to achieve this. So maybe in 1, 2, 3 months, we will be able to provide these results to the audience. All these results will be publicly available. All data will be published in a paper, and every group of researchers will publish their own papers. So, and I believe that this challenge provide and generate a great source of data and knowledge for this particular underdeveloped target. And I believe it stimulates a lot of research in this area and in this field. So thank you for your attention. And if you have some questions, I would be glad to answer them. Yeah, Karol.
The first one about the boron. Boron has quite a distinctive binding instead of carbon, because it's able to do a hydrogen bonding. So, what is your explanation why this works? Were the borons inside the structures and not interacting with something outside, so that it worked?
We validated this case on a very limited set of structures, because in PDB, if you will search for boron-containing ligands, you will find just 450 structures. and the majority of them are covalent binders. And there are only 50 or 60 compounds which are non-covalently bind. That's why in many of those cases, I believe boron does not create some hydrogen bonding. So that's why we observe such an output. Yeah, in some cases, of course, boron can create some specific bonds. And in this case, this approach may fail. But on this set of 55, if I correctly remember, structures, we got almost the same accuracy for poses reproduction relatively to the commonly used ligands. So 60%, something like this. Yeah, Thierry?
Yes, thank you, Pavel. Very interesting, and congratulations for these results. I was also wondering about the same thing as Karen with the boron. So you assume then an sp2 geometry for the carbon? A planar one, or which kind of atom type do you set?
It is assigned automatically by the software. So we just replace. We do not add any other hydrogens since they are not necessary.
But you have 3 bonds, right?
Yes, so I don't know, we didn't check which atom type was assigned to this carbon atom. But I expect that it should be sp3.
But then you would have another proton somewhere.
But all this software, it ignores non-polar hydrogens. So that's why it not interfere.
Okay. But it
So
doesn't introduce a charge then?
yeah. So it's also not sensitive.
So it's a dummy atom more or less.
Yes, yeah. Something like this. Some other, yeah?
Thanks for the really nice talk. It was a very interesting story. Congratulations on the results. I would like to ask if you, what computational strategy did the other top scoring groups use, and if you gained some interesting insight or inspiration from them?
They didn't fully disclose in details. They provide some general description in the beginning, because every participant should describe briefly what they wanted to do and how they wanted to achieve. But of course, these plans are usually changes, because we also expected something to do, but afterwards we did something else. They provided currently very general pipelines of what they applied. They used ultra-large docking as well. They used those deep docking which I told you previously with this, because this group, Isaev and Cherkasov, they use deep docking. So they iteratively dock compounds, train the QSAR model, rescore the rest, and iteratively select best hits. So more details, I hope, will be provided soon by the participants. At least they should be disclosed on this symposium finally. I would be even I would be even more interested in those approaches which were not succeeded, because successful approaches I believe will be pretty much similar. So they use docking, some structure-based approaches, similarity search, de novo design even also. But what are those approaches which are not so well? So maybe it will be even more valuable for us. Yeah, please.
Thanks for this nice talk. Are you planning to participate in any other cash challenges?
I would say that participation in cash challenge is pretty tough job. So it requires a lot of attention, a lot of efforts, and if you develop, because in this case we develop in parallel our instrument and perform these simulations. So it was pretty difficult for us. If you have already polished pipeline, it's pretty easy and really good idea to participate in cash challenge. In this case, you probably will not be in a rush, so you have more time to prepare. Nowadays, cash challenge already not for free, because only the first one was completely free of charge for participants. Now they ask to pay at least partially, to cover costs on synthesis and experimental validation of those hits. And it costs roughly something like 7,000 euros per participant. So theoretically we can participate, but this probably was the most challenging among these 4 which were already started, because in this case we had just the structure of a protein, nothing else. In later challenges, they provided already active ligands, because the targets were those proteins of SARS-CoV-2, which already quite nicely investigated. There are a lot of reference molecules, there are a lot of X-ray structures, and so on. So they are less interesting, maybe, less challenging for us. And this one was nicely correspond to our interests and our developments. That's why we decided to participate. So in future, yes, I think it's a perfect school for PhD students. Excellent. Because here you can validate your ideas, your approaches. So maybe at some future we will participate once more. But currently it's too tough. So we had to take a break, short break.
Thanks. And I have a follow-up question. Like, obviously you have mentioned this pipeline and you're planning to publish the pipeline, but can you publish like the whole cache challenge story, like as a research paper?
Yes, sure. So we are not limited on that. So as I understood from the preliminary discussions, there will be the joint paper of all participants who discloses their names in one publication, and every group can publish their own papers describing whatever they want, findings, pipelines, outputs. Because we also, I'm thinking that if we will succeed in these metadynamic simulations, which we now continue, and we will be really able to find some true binding mode in which I will believe to some extent, then we continue this study, we can design better molecules, we can order the synthesis, and we can also continue working in this direction as well. So I consider such an opportunity, but we will see what would be the output of those metadynamic simulations. So, because it is pretty interesting, it's really interesting, and it's a very challenging target for me. It's quite unusual, because it's just a pore with not so many polar contacts inside, not very flexible, but also not fully rigid. So it's really interesting target.
So I saw an arginine thing.
But it is outside.
It's outside.
So it's somewhere flow outside. It sometimes can go closer, further. So there are not so good polar groups on which we can anchor. It may happen if your ligand is large and it looks outside, because I'm still not convinced that the ligand fully goes inside this cavity. I think that it may just partially go inside and some part will be outside. X-ray says completely different, so it binds somewhere outside.
But the ligands that were found were looking kind of similar, right?
Yeah, yes, yeah. So they are almost some in a rod shape. So maybe they bind somewhere inside, but to understand this binding pattern, it's pretty tricky. So some other questions? So just 2 years story in 30 minutes. Okay, thank you. And I pass the microphone to Thierry Langer, professor from Vienna University.
Okay, so in the meantime, I will be leaving. So I hope you've enjoyed the workshop so far. We will send you the certificates and the online test as well. And also I will send you all the evaluation forms. So please fill it out so we can make 8 advanced in silico drug design even better than this one. Hopefully. So thank you and see you. And happy Woodbury.
Maybe a question. Is it advisable to write evaluation at the university form like evaluation?
No. This is evaluation which is needed by the elixir. It's much more developed.
What I can try is here this thing here. Just question for Okay, so sorry for this short break here. Thanks. So, ladies and gentlemen, I'm very sorry. I apologize for these technical problems here, and also the presentation is now in a program that is not the one that I used to make the presentation. So the fonts are probably messed up and things are not the way it should be. But let's try anyway. So I want to explain to you in this last part of this exciting workshop, and I'm really grateful to be here because I really love this workshop. Unfortunately, Karel had to leave already. I had a very nice discussion with him. So he and his team does a great job on that, and I'm really excited to come here. And today I will give you some overview on our latest developments in the pharmacophore approach. And I named this talk Next Generation Pharmacophore Modeling Concepts and Applications. And basically, it's the collaborative work of, first of all, people in my group at the University of Vienna, who are shown here in a snapshot from last summer. But of course, it's also people that have been working in previous times at University of Innsbruck, where I started my career like almost 30 years ago. And of course, people who are working in the company that I created together with 2 other colleagues 21 years ago, which is Intelligent, here on the right side, and which is the company who develops the software that we will be using this afternoon in the tutorial, which is Ligand Scout. So when we talk about okay. Yeah, before I start, I also have to acknowledge, of course, funding bodies who fund our work. And basically, we are, at the university, we are collaborating both with European consortia, like this new Innovative Medicines Initiative, but also with companies like Servier or Janssen, who we had projects with and developing together with the university group and the company Advanced Algorithm. And currently we are together with Johannes Kirchmeier, who you saw a few days ago, in a so-called Christian Doppler laboratory, which is funded by the Christian Doppler Gesellschaft, which is an Austrian funding organization, but half of this money comes from 2 companies. One is Boehringer Ingelheim and the other one is BASF. And with these companies and the people from the groups in Christian's, in Chris Ostenbring's, in Johannes Kirchmeier groups, and in my group, we also develop new methods based for better lead discovery, better hit identification, and so on. So we should never forget one thing here. This is very important, and I really liked the talk of Pavel before. You can do a lot of modeling and a lot of predictions, but if you don't validate them, it's worth nothing, right? It's really something you need to validate with experiments, your computational models. It's of course very good to have nice models, and nowadays nobody does any design and synthesis without computational support. This is also one thing that has changed over the years. 30 years ago, this was something that was very, very difficult to convince people to do computational simulations. Nowadays, everybody does it, and a lot of people learn about it. But it's still important, again, to do this validation using experiments. And one thing here that is this story is actually to find the needle in the haystack, right? If you look for new chemical entities that you want to test on a certain target, it's like looking for a needle in a haystack. And this is true for hit identification, but this is also true for hit-to-lead expansion and lead optimization. You have a huge chemical space to choose from. The question is always where to go in the most, in the best possible way to achieve your goals. And I remember many years ago, there was a person, a French medicinal chemist, who said that it's not maybe the best idea to make the haystack bigger if you want to find a needle, right? And now this is just what we are exploring. People make the chemical space bigger, they accept the available chemical space, and claim that the hits will be better. I am very curious about the outcome of these things, right? If we can screen in the billion chemical space, we should be able to find then the best compound if it's there in this whatever 60, 70, 100 billion compounds. But then we really have to enumerate all of them. It makes no sense to make a pre-filtering and narrow down to some 100 millions maybe, and then do the accurate screening? No, because then you will go next to the hit. If you want to find the compound, you need to have them all there and have a method that is precise. And so we are also engaged in this. Now we are trying to elaborate on pharmacophore-based enumeration of large libraries and virtual screening, and we'll see. We do this together with a pharma company at the moment. So let's see. The most important question is, of course, both related to data analysis, so which molecules to choose for biological assessment, how to modify these molecules for optimizing their properties, how to build models for reliable medicinal chemistry decision support, and how to design molecules void of toxicity risk if you want to go into drug discovery. And it's about data representation, how to guide the analysis of MD, of molecular modeling results, and also how to make use of MD trajectories. And we see more and more MD done, and also Pavel showed very nicely here. It started with this metadynamics. So it's a huge new way of analyzing proteins, but how can you take information out for your design out of this? And I will try to show you our ideas. So a possible way to do this is to compare compounds in view of their preferences for specific molecular interactions. And you can do this here using a so-called pharmacophore model, annotate molecules with all interaction features possible. So this molecule here and the features projected on this molecule would be all potential interactions that this molecule could do in a binding site, if the protein has all these possibilities. If not, of course, you need to find out which of them are really the important ones. And you can do this both in a ligand-based approach and in a structure-based approach. And for instance, if you have a structure of a ligand in your protein, you can consider only those interactions of the ligand with the protein binding site. And so when you look at all them, and then you can look at the protein, you will see that a few of them are just not necessary at all. And only those features that are listed here now are those who are characterizing the interaction of this ligand with the protein binding site. And each ligand will be a little bit different. But these pharmacophore features are a little bit fuzzy. So they have spheres and vectors with tolerances. And so the idea is to describe a molecule based on the interactions it can make with the protein. And again, you can derive this in a direct way, directly from an X-ray structure, from a cryo-EM structure, etc. So a pharmacophore, and I'm not sure if this definition has been shown here already. This is the official definition of the UPAC. Says that the ensemble, a pharmacophore model is the ensemble of steric and electronic features that are necessary to ensure optimal supramolecular interactions of a molecule with a biological target and trigger or block its biological response. And this guy is Camille Vermouth. He was a very famous medicinal chemist in France who brought several molecules to the market as an academic teacher. And he was using this approach very, very successfully. And this was also a sort of trigger for me to go into this field. So we can look at feature-based pharmacophores as the totality of universal chemical features that represent a defined binding mode. And these features can be electrostatic interactions, H bonding, hydrogen bonds, right? Aromatic interactions, hydrophobic regions, but also coordination to metal ions. Also coordination of halogen atoms to lone pairs in the protein, and so on. So this is a whole sort of description in three-dimensional space that you can use to compare molecules with each other. On one side, to get ideas how to modify a molecule to make it better for a certain pharmacophore, or also to make it less good if you want to avoid a side effect. And I believe strongly that pharmacophore models are the most suitable data representation methods for guiding medicinal chemistry, because in medicinal chemistry, you want to know your molecules by interaction. And you want to know how you can make a molecule stronger by making more interactions with your target, or less if you don't want to hit a certain anti-target. But any interaction of a molecule can be encoded in pharmacophore interactions. And this is why I'm so fond of this, and I believe it's really, really powerful. And so I said already, we developed this software over 20 years. It's called Ligand Scout. I guess it's really the most complete and best performing pharmacophore method, structure-based and ligand-based. And now I look every month, so the number of papers is growing steadily. So we have around 3,200 papers where people have used the software for structure-based modeling, ligand-based modeling, virtual screening, and so on, hit identification, and you name it. So you can just look at in Scholar, google.com, and you will find all these interesting papers. Every month something comes out. And so I'm very happy, of course, about this. And I just want to share with you two very recent success stories from this software here. This is one paper that has been published by Pfizer in JMed Chem recently, and where they discovered in their own library of molecules. So this was a molecule that they had in-house, and they have something like 4 to 5 million compounds, and they don't screen them all, because also Pfizer, when they do a high throughput screening, they make a subset and screen maybe 1 million out of the 5. And so this compound, they were working on this hematopoietic progenitor kinase 1, and they had never found this molecule before, and the last resort was to make a structure-based pharmacophore using Ligand Scout, and they came up with this hit from their own library. And this hit was really good. I mean, look at the affinity here. The hit had already an affinity of 17 nanomolar. So this was an ideal starting point. First of all, they have the chemistry in-house. They know exactly what they can do, patented already, or not patented, but not known for others. And with one change here, adding a chlorine atom here in this position, they made the lead compound, which was like 2.9 nanomolar, and had a very nice selectivity to other kinases. And this was then further developed. It's not yet published, but they told me they will come out soon with the paper with the clinical candidate. So this is a very fast and I would say enormously successful way to discover a clinical candidate, right? From a hit to a lead with one change and then another few changes for the clinical candidate. And another paper from a Japanese group that I really like a lot is this paper here, the design and synthesis of DDR1 inhibitors using deep generative models for generating new compounds. So what they did is they used the reinvent molecule generator. So this is a method that is freely available to everybody. You just need a sort of scoring function that you train the method with. So it starts with SMILES from Campbell, so molecules that should be synthesizable, that should have biological activities. And you generate molecule after molecule with this technique, and you score the molecule with a scoring function. And these people took a structure-based pharmacophore as the scoring function and were giving a high score for molecules that would fit nicely to this model. So what happens after a while, after several epochs, your scoring goes up, and because the system has learned what kind of molecules will fit this pharmacophore model. And then they generated several thousand molecules, stopped, and then they did a binding affinity ranking, also using the Ligand Scout tool here. We will show you this in the afternoon. And decided to synthesize something like 12 or 13 of the top-ranked compounds. And 9 out of them were active, and 1 was in the dual-digit nanomolar range, and this was this molecule. And so they know what, just without having anything at the beginning, using a structure-based pharmacophore, generating new molecules, synthesizing, testing, they got this nice hit here from the beginning. So I really, and these are just 2 examples out of these 3,200 papers that are relatively new and that I really like. So now to go back to the model, how to rank pharmacophore features. So you get a model that has maybe 10 features, and this is also the strength of our software, that it doesn't go down by speed if you raise the number of features. So normally this would be the case. Normally you would try to avoid feature-rich pharmacophores because the screening gets really slow. And in our case, the screening gets faster the more features you have, because we have a very smart indexing in our databases. And so the question is, all features have the same weight. So we don't do a discrimination of feature weights at the beginning, and we wanted to have a technique where we can also predict binding differences like for instance predicting a KI value or an IC50 value based on pharmacophore features. And so this the idea was to look into literature. There were already a few methods out there from Schrödinger. Schrödinger has phase, the phase pharmacophore modeling tool, and BioVia, earlier Acceleris, has the Hypogen method here. Both are pretty much limited by the number of features that you can use. So for instance, Hypogen can have a maximum of 5 features and only 1 feature per atom, so it's really limited. Same is more or less true also for phase. And we wanted to do better here, and we developed a method that starts actually with the so-called Grail-based pharmacophore technique, which I will explain just in a few slides later, where we do a hotspot analysis around ligands based on a grid. So we put a grid around all the ligands and calculate pharmacophore heuristic probabilities, actually. And then we generate this merged pharmacophore out of it. And then we do a clustering and feature selection and put weights on the features. And this method now has been published. It's available also on GitHub, so you can run it outside of Ligand Scout if you like. And if you are agile enough to run this software from GitHub, so it's not an issue. Here are a few steps. I don't want to go too much into the details. It's all described in this paper, but what you get at the end is a post-processed pharmacophore where the features have got weights, and the weights are depending on the importance that the machine learning discovers during the training phase. So actually you need to have active molecules with activity values or affinity, Ki, whatever you want, any property, and you can then correlate this property using, it's a pretty simple random forest approach once you have the model, to get the weights for each of the feature. So it's just listed here. So, and we have also then implemented a method where this goes more or less automatically, so you can present your training set, it will go the whole process automatically, and you will get several models that you can then evaluate later on their capability of correctly predicting bioactivity values of new molecules that you don't have used for your training. And we have also implemented this in a convenient KNIME nodes implementation. So KNIME is, I don't know if you have been using KNIME here in this workshop. Not yet, but something very interesting. So this is open source. You can download, install. This is a pipeline software, and a lot of different people have presented nodes that you can put together. And there are also some commercial vendors who offer their nodes in the KNIME platform. The advantages of KNIME is that you don't need to be able to script yourself, so it's a kind of graphical user interface where you can connect specific workflow nodes to specific protocols that do the things that you want to do. And for instance, we have one workflow here that generates your QFAR model, so you can write it, you can read it once it's generated, you can use it for prediction, and you can use it also for generating the model. So this would be a workflow here, and it's also available on GitHub, where you can run your quantitative pharmacophore prediction. So why did we do this? This was basically in a program that was funded by the European Community. It was called NeuroDerisk, and this was a big consortium that I was coordinating. I was lucky enough to get this and coordinate it between academia and industry. And so we had like 5 big pharma companies who contributed with their data on neurotoxicity, and then we had companies who did models. We had academic groups who did models. We had academic groups who did not only in silico models, but also in vitro and in vivo models. So we have a whole set of new biomarkers for neurotoxic compounds new in silico models that will predict if a compound has a risk of neurotoxicity. And this can be suicidal ideation, can be risk of seizures, can be peripheral neuropathies, and so on. And it's aimed actually at getting better compounds with less risk of toxicity. And what we did in this program, we generated pharmacophore models, so-called neurotoxicophores, for all these different aspects here. Sorry, it was too fast. And here, for instance, we have this quantitative neurotoxicophores for GABA A ligands. We have here are the list of molecules, the data sets that we used from Campbell and together validated with industry data to be able to correctly predict if a molecule has a certain chance to bind to this GABA receptor in an agonistic way and then elicit, for instance, seizures. Right? So this is a typical thing. If you bind to the GABA channel, you will have the risk of seizure. One thing, now we can predict this. Okay, enough of this static stuff now. I want to continue here and go to the view of dynamics and how to connect dynamics with pharmacophores. And this is a nice picture from an Italian site. It's Siena, close to Siena, it's the Certosa di Pontignano. There's always a very nice conference there. And I was lucky to be able to take a few pictures, but they would not show now. But I took this picture from a video here, and you see the birds coming out of this tower, and they fly through the video now. And normally I would show first the birds and then the video, and no, it doesn't show, unfortunately, on Windows. So the idea is to show you that there are different frames that are difficult to get normally, but if you have the whole video, of course you can stitch them out. We can do the same thing with MD simulations, actually. And we look at, and this is also what Pavel nicely showed at the beginning, he did this metadynamics, and then he took several frames to start the modeling with. We want to go a little step further here, and this is also a nice paper here that shows the impact of MD simulations in commercial drug design and commercial drug discovery. So it's not only anymore an academic thing, it's also done in industry more and more. And so MD simulations get more and more attraction because computer power is better. We have now the GPUs, we can run large-scale simulations. We have new techniques also, like this steered dynamics. The question is still, how can we interpret this huge amount of data, the dynamic data, not only taking a snapshot here and there, but really look at the whole trajectory. And we believe that pharmacophores might be a good solution for this. And so we have implemented in Ligand Scout the way to analyze MD trajectories in a dynamic way by generating pharmacophore features for all the frames of your dynamics. And this is not limited now only to a ligand. You can look at any kind of region in your protein. For instance, yesterday I was in Paris and people asked me, could I analyze an antibody binding to an antigen? And yes, you just need to have the simulation, and then you define one part of the antibody, for instance, as a ligand, a certain sequence, and then you run your analysis and you see the pharmacophore, and you can directly look at the interactions of your protein with the other protein. In this case, we looked at the interactions of a small molecule with the binding site. But you can look how a molecule gets into the binding site, where it gets stuck, what kind of interactions are there, for instance, and so on and so on. So there is a huge amount of information that is hidden in this that can be made available now in a pharmacophore way. And these dynamic pharmacophores, I think, are really a key for interpreting in a new way MD simulations.
Which MD software you support and make it possible?
Yes, actually, no. It's at the moment we support the GROMACS, AMBER, and CHARM. So these three formats like GROW, XTC, and what is this, DCD, we can read in. So there is no generation of MD in LigandScout, but you read in the trajectory and then you do the analysis. Yes?
That's just a follow-up that if it works with one format, then you can convert any dynamics to that format and it works with anything.
Yes, exactly. So if you, yeah, of course you can. If you even so, we cannot read in the Desmond format because it's not an open format. But and Schrödinger has not described it, and so we don't want to reverse engineer this whole stuff. But you can convert it using NAMD, for instance, to any other, or VMD to any other format, and then you can read it in. And then you can do some analysis. And here I show you a few examples, and we can do these things in the afternoon also. So here is a sort of frame versus time and occurrence of pharmacophore features. So here you have the unique pharmacophore features here that occur all the time, over and over again, and you see where they are. So one is there all the time, for instance, this yellow one, which is a hydrophobic. And another hydrophobic is there all the time, but here is a little bit less. And then some of the features go down and are not present, but come again. And the idea is you see the features as, for instance, H bonds, right? And if you would have to look into distances in your trajectory, and you look, you know, for instance, there's an H bond between the atom 1 of your ligand and some amino acid of your protein. But all of a sudden, this H bond moves to another amino acid, but it's still an H bond. So the distance to your first atom would be too far then to recognize that it's an H bond, but the H bond is still there, it has moved. So the idea is to really look at the interaction, not anymore at distances, right? And then I know this feature is there, and I can follow it, and I can select then, for instance, here, I can select a certain feature. I selected this H bond here, and I can see all the pharmacophores here that contain this feature. They are colored in green. And then I can directly click on this bar, and I will see all the pharmacophores that have been recorded where this feature is. And on this diagram here, I can see the amount which H bond acceptor, for instance, is doing with which amino acid. 53% with this one, 42% with this water, etc., etc. And it's correlated actually with some other amino acids that are doing other interactions. So it's a complete overview on the interactions of your MD trajectory in the pharmacophore domain, but giving you immediately design criteria for your optimization of your ligand, right? And it would be very interesting, Pavel, if you maybe would have time and interest to look at this from your MD trajectories of ligands that you did, if you could learn something from there. Could be interesting to see. So, using these MD trajectories, we can find, I believe, relevant pharmacophore models and define ways to calculate similarities, sample and identify rare but important events, and using them really in a way to abstract, to give abstract ligand-protein interactions. And so what we did is, we then developed this so-called GRAIL method that I showed you before already when I talked about quantitative pharmacophores, because this GRAIL method can also be applied, of course, to MD trajectory. And this method you will find in our toolkit here that we make available as open source toolkit. It's the CDP kit. And here's a website, so its documentation is on the way. It's not completely documented yet, but there's a lot of, so it's Python, a Python API. It's written in C++, high performance, high stability, and there are also some binaries that you can directly use in your scripts. And one of these things is this, this GRAIL, the grids of pharmacophore interaction fields that we used to characterize MD trajectories from the other way around, without looking at the ligand, but only looking at the protein, to find pockets and describe the pocket's characteristics. Which kind of features could a certain pocket fill, right? And so this was done in collaboration. So just a few words here how we do it. We define first, of course, a certain key amino acids that need to be fixed, because in the trajectory the whole thing will move, and we generate a grid on each frame, and for performing these grid calculations then we need to align them again to have them all in the same coordinate space. So we do this by defining some residues here, and in this case it's this HSP90 case from Doris Schütz, who had a lot of trajectories. We use these things, and then what we do is we calculate, we then generate our grid, and on each grid point and for each pharmacophore feature we calculate a score. And the score defined by distance and angle, so depending on the feature. So if you have a direction like an H-bond, you can have a vector. If you only have a spherical function, you only have a distance. But we can then, using this method, for each point, give a score for each pharmacophore feature. And we can rank them. And then we know exactly which point in this grid is the best point for making the most strong hydrogen bond, for instance. The second one, the third one, so everything is ranked. And then we can, so the function that we use is a generalized Bell function. It's not a Gaussian, but because it's a little bit steeper. It works really well for this. And then we can look at these interactions. And so here we look, for instance, at a phenylalanine here. And we see the regions for aromatic interactions, for aromatic hydrophobic interactions, or hydrophobic and positive charge aromatic, without having to look into the ligand site. It's only based on the protein and on the movement of the side chains and the backbone. Same thing for negative positive charge, aromatic positive charge, and H-bond acceptor, H-bond donor here, DEF. So each amino acid, you can see, creates some areas where the amino acid wants to have some interactions. And the same thing goes also for instance, for this aspartate here, where we can see regions H-bond donor, H-bond acceptor, and positive negative charge. So we have a whole picture of the trajectory based on pharmacophore interaction probabilities. And now we can look at the pockets, and we know exactly what kind of things you would like to have in this pocket to make optimal interactions, right? So this is the idea here. So you can then really transform this into design guidance. So you can focus on specific regions, for instance, looking at water molecules. This is very important, water molecules that might be entropically disfavored, and you want to replace them by a small hydrophobic part, like a methyl group. This is this typical magic methyl. Or you can do this pharmacophore hotspot frequency analysis to prioritize replacement and modification of molecular substructures. And of course, this is easily adaptable for automatization. So you can run a generative molecule builder and use this for also as a scoring function. And the last thing I want to show you today is this kind of way where we try to understand the relationship between pharmacophores in a trajectory, in a molecular dynamics trajectory. And this was the work that was done by one of my latest PhD students, Arthur Garon. He focused on the way to understand relationships between pharmacophores in a trajectory. So which model is related to which model, and can you get a sort of idea on a tree, which is the common ancestor pharmacophore, and where do all the different pharmacophores go, looking at the MD simulation. So actually it's a so-called hierarchical network of pharmacophores that we built. And the network is where the layers are organized basically by multidimensional scaling. Each node in this tree represents a unique pharmacophore model, and the nodes are sorted in a way to best represent the distance between them. And the distance shows how close they are. Close in distance means they are very strongly related to each other. Far away in distance means that there is no real relationship, direct relationship, but maybe via other models. So the fingerprint space is reduced to one dimension, and again here the distance between the nodes is then defined by a Manhattan matrix. I just want to explain this a little bit in more detail. Let's look at these 5 models. So each of these pharmacophore models here are fed into a fingerprint. And so here you see the color. This is hydrophobic. Yellow, red is H-bond acceptor. Green is H-bond donor. And so we create this vector for each model, and we tell, we feed a 1 or a 0 if a feature is there or not. So what we can then see, so this would be these 5 models here, A, B, C, D, and E. And we can do this, and then we can see that some of these have the same pharmacophore vector. So D and C, for instance, have the same features, the same vector, so we can make it simpler already. So this, we counted, it happens 2 times, but we need only 1 vector, right? And then also what we can continue this game here and see E, for instance, is the same as B, and we can also then remove E. So then we have 3 pharmacophores here, A, B, and C. Now, there is, of course, a relation between B and C and between A and C, right? So if you look here, between B and C, there is, for instance, this donor missing here. C has the donor, but B doesn't have it. And A does not have this second hydrophobic here, but other rest is the same. So now, can we make a relationship? So the relationships between these 2 and these 2 are clear, but how is the relationship between those 2 models? So in order to make the matrix full, we need then to create artificial pharmacophores, right? So this is the relations, and to make a relation between B and A, we need to create another vector. But this is an artificial one. This is not one that we have seen in the dynamics, right? So this is also an interesting thing. And then we can put this all in this distant matrix and flatten it down and project it. And then we can see here, A is related to C, C is related to D, D is related to B. And how far they are from each other means how big is the distance. So in this drawing, it's just averaged here, but in reality, you can, of course, scale this correctly. So then we know that vectors who have been counted several times, we can make the node a little bit bigger. So B and C have been seen 2 times, as you remember. So we make the blob a little bit bigger when we do the projection. And then, so the frequency would be the node size. The hierarchical link would be then the subset and superset of pharmacophore features. And then we can project this in a sort of tree where we see now the model D, the model B, the model A, the model C. So A is seen 1 time, B and C 2 times, and this has not been seen at all, so therefore it's another color. Again, we can project it on this y-axis, and then we can make a nice diagram here where we additionally on the x-axis plot the number of features, and on the y-axis we have the distance projection. And now we can really build a complete tree out of this. And the more we go to the left, to the 0, we will have a feature. This will be the pharmacophore with the common ancestor feature. We can really count, it is 1 feature normally that all of the other models have. And the more we go to the right, is the more specific pharmacophores we will see. And they might not be related to each other when we go into the whole thing on the picture on the right side. And so this is a typical diagram that we get, right? So this would be the most like comprehensive models here. They have like, this would be 1, 2, 3, 4, 5, 6, 7 features. This would be 6 features, 5 features, 4 features, 3 features, 2 features, and 1 feature. So this is the common ancestor. And we can go through all of them and check exactly which pharmacophores they go through to come from here, for instance, to here. And there is not only one way, there might be several ways. But this gives you already a sort of relationship of these pharmacophores to each other. And again, here the size means that these models here come often very frequently. So these ones are the most frequent models. These ones are a little bit less frequent, and the smaller the blob is, the more rare these pharmacophores are. Now, how can you use this? What can you do with this? You can look at all models you can use, for instance, for virtual screening. And you can rank them according to their AOC. How well are they able to discriminate true actives from false positives? So this is here, you see, for instance, that this one is a little more green than this one. This is already a little bit low. So even if this model has more features, it has a slightly worse area under the curve than this model, who is one who has one feature less, but is more selective and better in representing the true reality. So this is one way to analyze this. The other way, of course, you can also do a pharmacophore clustering here and then see if they belong to same families. And this one does not belong. And when you look into the details, there is no line that goes from this model directly to this one. So they go around each other, but there is no connection. It's clear because you look now at the pharmacophore cluster, so they belong to different clusters. Also interesting. But the most interesting thing happens, and I can skip this. This is nothing more here. When we look at one protein that can have different overall conformations, like not foldings, but maybe an open state and a closed state, an activated state and inactivated state. And you look at the dynamics of different ligands in the same protein. And this is what we did here. And this is this case, Arthur published this also here this was the pentacle of his PhD, actually analysis binding modes of ligands in human glycokinase, the difference between the active and the inactive form. And you see here at the end, there are two different distinct pharmacophores here. One here and one here. And one is for the open and one is for the closed. And it's clearly shown that the dynamics is able to dissect these events here. And again, here we see the active form and the inactive form. The selection here, so here is the active form, and here's the inactive form. And also the pharmacophores look different. They are all present in the trajectory and somehow related to each other, but they go into different directions. And now when we want to find molecules that will stabilize the inactive form, we just will select pharmacophores here for screening. If we want to find molecules that stabilize the active form, we will take pharmacophores from here for screening. They are different, right? And so this is the way to take advantage of these MD trajectories in a very directed way here. Yeah, so again here, you see here colored now the pharmacophores for one and for the other set. Again, a little bit more visible. Okay, so I hope that with this information here, with this slides, with this presentation, I could convince you that this pharmacophore approach is very useful, not only for hit identification. We know that for hit identification it works really nicely, especially with respect to speed and accuracy. So I believe that we will be able, after a while, to really screen billions of compounds with pharmacophores. So it's highly useful for hit identification. But it's also useful for analyzing MD trajectories when you do a lot of effort before you synthesize new compounds, especially in hit-to-lead expansion and in lead optimization. So it's really highly useful for lead structure optimization because, again, it gives you the connection between the structure and the interactions in a dynamic way. And with this, I want to thank you for your attention. Actually, there is the website of my group is cheminfo. CDP kit can be downloaded, and if you're interested in the software in Ligand Scout, this is commercialized by Intelligent, and we will be able to play with this software. You have a license here for free for a while that you can use it. And I'm not sure if I have, yes, I have here a sneak preview on Ligand Scout Next. So this is the software that we are currently have in pre-alpha state, where we have already a new database format for high exascale screening. So we have started now to build the first library with billions of compounds and are exploring the performance of this. So it's a completely revamped technique behind. And also, so there is also some changes in the graphical user interface. It's still, I believe, user-friendly. It might be a little bit more complicated in the future, but there are some good things here, for instance, that you can run several binding sites in parallel, that everything is a united data model, so we don't have anymore to copy things from one perspective to the other one. No, everything is in one perspective. All the data is congregated in this one perspective, and we can do operations, for instance, in parallel here for all these perspectives. And of course, this is a screenshot taken from a small laptop monitor. But if you have a big screen, you can have like 16 binding sites next to each other if you like. So I'm very excited about this, and I hope that we'll be able to have a beta version soon. At this moment, we are running it also on the high performance cluster already, and the results look promising so far. So I'm very excited about this. And with this, I'm finished with my talk, and we will have some break now, and then we will have the tutorial.
Probably we have some questions.
Oh, some questions, of course. Yes, Martin.
You were saying that during molecular dynamics, some of the pharmacophore disappeared. So does that mean either that it disappeared from a space or a sphere defined in the beginning, or it means that in some pair interactions?
No. It's some interactions disappeared. Interactions. That's not the whole model, but some. But if you look at the pharmacophore model and you say, okay, you have a limited number of unique pharmacophores, right? And the unique pharmacophores are more or less derived or determined by the ligand. So at a certain stage, the ligand can make most interactions with in a certain configuration. Then there are some configurations where it does not make all interactions. So this is what I said with disappearing, and then yeah, yes. Thank you.
And the software is written.
Yeah.
Software is written in Java, right?
Ligand Scout is in Java, yes. Java at the moment is Java 17, I think. That is, yeah. And some parts are C++. The real, I would say, where it's important to have high speed is C++. In minimization, I think there's parts in C++. But the advantage of having it in Java is that you can run it on Mac OS, on Linux, on Windows without having to change too much, right? Yes?
Is the creating binding site a pharmacophore?
Yes. It's recognized normally as a covalent function, so there's a specific feature for that. It's an orange sphere. We do not use it in the screening. So because you have so many potential things that would attack, that we switch it off by default in the screening. Always, yes.
For example, if it's acrylamide,
yes.
you can definitely say that it will
Exactly.
It will click with this thing.
Absolutely. So
Why
we
would you turn it off?
just in order to ask the user to be smart and and recognize it. Yes. Yes.
You also implement some command line API to...
Yeah. So in Ligand Scout there are, and I will talk about this afterwards, there are some, I think around 15 or maybe 10 to 15 command line tools So screening can be command line, ligand-based pharmacophore generator, structure-based pharmacophore generator, affinity prediction, aligning, clustering, and some more. So you can really run scripts, but you also can run, so there are also KNIME nodes where you can use predefined functionality in KNIME, yes. Yes?
The Ligand Scout is available only by license, right?
Yes.
And for any licensed software, there is always an analog. Do you have concurrence?
Of course, I mean, of course, of course. No, we started to build Ligand Scout 20 years ago because we were not happy with the existing software that were out there, and there was already Moe had pharmacophore features, Catalyst, which later became BioVia, and Phase, and these are the three, I would say, commercial competitors. But we went out to make it better, and actually we had some customers who replaced their pharmacophore solutions with ours. So Sanofi, for instance, we collaborated with them on specific aspects to be able, so that they were able to get rid of the other software. Yeah, and so there is for academics, it's really, I mean, it's I would say if you are a student and you ask to support to get a student version, they will give you repeatedly evaluation licenses. But what the normal case for academics is that you get a license and then you have unlimited activations. So you can, also students can run it on their own computers. So this is, and I don't know, I'm not involved in the business, I'm just in the strategic team. But I don't know what it costs, but it's not expensive also for academics. So they make their money with industry.
Other questions?
Yes?
I have a question. If the NeuroDRX tools you've been talking about, if they are available for free or for academic users, or if it's proprietary?
Actually, this is proprietary at the moment. It's only available for the consortium. It's still under development. The project is finished, but it's still being refined, and the consortium partners have access to it. Now, if you have a good reason to ask, you can write to support and ask if they will give you a license. And it's not excluded that they do it, right? It's also possible. But this is so that the NeuroDRX tools are in a KNIME platform. And so when you go to the website, actually there is a pretty, this was done for the consortium, but it's open to the world also, so you can see how the things are deployed. So there is like, it's a profiler, it's called a profiler, and this profiler connects to the database of models, and so that the models can be updated constantly. So this is not locally installed, so it's still on the servers. And once you start this, you select the models that you want to use, and then it downloads them, and in your node it will do the profiling and tell you, okay, there's a risk for this and this and this neurotoxicity.
I think it could be very useful for one of our projects.
Yeah, of course. Yes, just you can send me an email and we can discuss this. No problem. Yes.
You said that the interaction between antibody and protein can
Yes.
be described just like as a small molecule.
Yes. Yes.
Is there a limit of pharmacophore groups which can
No.
be taken?
No. No. This is the great thing. There's no limit.
Okay.
There's no limit. And again, the more features you have, the faster will be the screening.
Yeah.
That is not for sure because, I mean, yes, if you ask a full match, of course. But still, this alignment is tricky normally, and we have implemented a very fast method that is pattern matching rather than graph matching, and we believe that this is the way to do it. Still, the question is now, if you have like a pharmacophore with, let's say, 30 features, and you can screen 100 million of compounds probably in 10 seconds, because you will have no hit. no compound that will fit all these features, right? Because it's too big. But what we did one day is we decided to do a fragment screening. So you take your pharmacophores and you put it into fragments, and then you screen this part, you screen the next part, you screen the next part, and then you combine the hits that you get. And we did this experimentally, so we synthesized molecules, and we got interesting hits in a very short amount of time that were new because there was no compounds in libraries, so this was just fragments that we connected to each other, and it worked. But maybe when you have this huge library of whatever, 50, 60 billion compounds, and they are also large, maybe there are the hits there, yeah? Could be, so. No, he says no. Yeah, but the good thing also with the next generation of Ligand Scout, you can ask for a minimum number of features that you want to match. And it will not be slower. In the current version, when you do this, it slows down extremely, because it needs to take into consideration all possibilities, right? But we have changed the alignment algorithm now, and in the new version, it doesn't take more time, or maybe 5% more time. And this opens up completely new avenues, especially for apposite pharmacophore modeling, when you don't know which are the features that you want to see. So is there an X-ray structure of a PDB structure of this cache challenge now?
Just a protein.
Just a protein. So it could be interesting to look at the apposite model and.
I expect that Gerhard Vogler participated in this challenge as well.
Okay, he did. Okay.
Probably he used this approach.
Okay.
He didn't somehow label.
Okay. So I didn't participate. I have no time for this. No, but great. So anyway, we can. Yes, there's one.
Ask you for a consultation since I'm not able to install Ligand Scout onto my computer.
Yes, sure. What is? So what operating system do you have?
I had troubles in lessons and then even now.
So what operating system do you have?
OS.
Mac OS, okay.
Maybe afterwards.
Yes, yeah, we can.
One question regarding today's viral party. So who will want to attend? Just to roughly understand the number of people. 1, 2, 3, 4, 5, 6, 7, 8.
9.
9, 10. So perfect. Okay. Then we are secure. Because I wanted just to adjust the number of places.
Okay, so now we'll have a break for 15 minutes.